Okay, so here's the situation in Compton scattering. You have a photon of energy E coming in, and we're setting this up so that it's coming in from the left along the x direction, and it's going to collide um, with a particle of mass m. And in the Compton's experiment, this mass was actually an electron, but at the moment we'll just call it a generic mass m. And the the photon scatters. That is, it collides and bounces off in a different direction. Okay, and the direction has an angle phi. The new direction has an angle phi theta with respect to the x-axis, and it has, in general, it has a different energy. Okay, as the initial photon energy, so it's changed its energy, so it's E prime, and then the mass, the particle basically gets kicked down at some angle phi, um, and so it's going to have some obviously some kinetic energy and some momentum. So we know that the mass has to get, if the photon gets deflected upward to the positive y direction, then the mass has to get deflected down by some angle so that the y component of the momentum is conserved. The 3 momentum is conserved because before the collision there was no y component of the 3 momentum. That is, it was 0, so it has to be 0 afterwards too. Okay, so let's write down the expressions for the 4 momentum before and after. So before, we have the 4 momentum of the photon. We'll give it a we often give photons symbol gamma. So this is not the gamma factor that we talk about in special relativity all the time. And so it's got energy E over c, and it also has momentum E over c, and we've set it up so that it's in the x direction. So the other two components are 0, and then the mass here, or the electron, okay, has 4 momentum mc, okay, and we're in its rest frame, and so it has no 3 momentum components. They're all 0. Now if we look afterwards, then the 4 momentum of the photon after the scattering event is equal to, the energy is equal to E prime over c, and or the energy component is E prime over c, and then the 3 momentum in the x direction is just E prime over c times cosine theta, and the y component is E prime over c sine theta. And of course we're basically assuming that this whole interaction happens in the plane which is at z equals 0, so we don't have to worry about z at all. If we look at the electron for momentum after the collision, then we have it's basically the total energy is gamma mc, so it's obtained some it's moving now, so we have to add its gamma factor, and then its momentum is gamma mv, but in the x direction it's cosine phi, and gamma mv sine phi, okay, and then 0. Okay, so that's basically those are the four momenta before we started. And of course, this here, the sum of these two is the total initial 4 momentum, and the sum of those two is the total final 4 momentum, and it must be conserved.